Hey there, in this video we're going to continue our study of U-substitution, but before we get into more examples, I wanted to just review all antiderivatives that we've covered so far. And so I have the list written here. We have the general power rule, and then all our antiderivatives. So this is if you see a problem and it's just like, can you just look at it? Then this will be examples. So if you have something where you can use the general power rule, like x to the 7th, x to the 1/3, x to the -5, something like that, then you will use the general power rule. E to the x, we know how to do that. E to the kx, we know that we always get the exponential back and then divide by k, or you can think of it like I wrote here, multiply by 1 over k, where k is a constant. The integral of 1 over x, right, this is the one you do not want to write as x to the -1. We want to recognize that the antiderivative of 1 over x is the natural log of the absolute value of x. And then b to the x, an exponential where the base is not e, you get the exponential back, so b to the x divided by the natural log of the base, and then always plus a constant. And the nice thing about antiderivatives, right, is that you can check them by taking the derivative of your answer. So whatever you think your antiderivative is, take the derivative to check it. And then the trig one. So the integral of sine is negative cosine. The integral of cosine is positive sine plus e. Integral of secant square, we should recognize that as the secant square is the derivative of tangent. So the antiderivative of secant square is tangent. And then secant x tangent x, the antiderivative is secant x. Cosecant cotangent, the anti is negative cosecant plus c. And then we get into our inverse trig. So 1 over 1 plus x squared, the antiderivative, that is inverse tangent. So you can write the two different notations, tangent inverse of x or arctan. And same for this one. These are the two that are the most popular. If you have a negative, like if this was a part of a much larger expression, you had a minus in the front, you could also say that this is secant inverse. If this had a minus, the one down here, you could say is cosine inverse. But if you factor the minus out, then they're inverse tangent and inverse sine. And then we have our hyperbolics. So sinh and cos are the ones that come up the most. So I've just kind of wrote the hyperbolic sign in here. And so I put a star over here just because sometimes you might see things that are kind of look like an inverse tangent, but it's not quite, because this has a 16 in there instead of just the 1. So how do you solve something like this? And this is where you could use a little bit of U-substitution, right? We can rewrite this as 1 over 1 plus, what do you square to get 16x squared? 4x. Quantity squared dx. And now we can apply a slight U-substitution. Let u equal 4x, and then du is just 4 dx. And then one way you can think of it is like, well, I don't have a 4 in here, so you can put it there, right? So you can say times 4, but now I've changed this quantity, so you have to put a 1/4 out here. And so when you substitute, this will then become 1/4, the integral of 1 over it'll be 1 plus u squared du, because now your du is 4 dx. So this 4 dx will be your du. What I did in the prior videos is I was solving for just a dx. So my dx, another way you can think of it is 1/4 du. And so notice that we still get the same integral. And now I recognize that, oh, this is the inverse tangent of just u, because now I have just the 1 in front of the squared term. So this will be 1/4 arctan of u plus a constant, and then do your substitution again. What was u? U is 4x. So this will be, my final answer will be 1/4 arctan of 4x plus c. Or if you want to use the inverse notation, we can write this as 1/4 inverse tangent of 4x plus c. So both of these are the same. It's just choosing what notation we want to use. All right, let's go on to more U-substitution examples. All right, let's try this first example. The integral of 5x squared times e to the x cubed plus 5. And so first of all is, can we do it just by looking at it? So you want to ask yourself the question, right? Can I use any of these? The general power rule, is it just an e to the x? Is it an e to the kx? Do I see any of the antiderivatives that I recognize just by looking at it? In this one we can't, right? Because it has the product of two functions. We have 5x squared times e to the x cubed plus 5. So it's not just e to the kx. Even if the 5x squared wasn't there, I still wouldn't be able to do it, right? Because it's not e to the constant in x. This is e to the x cubed, so I would need something more. So this is a good example of U-substitution. So if we can't do an integral just by looking at it, then we try U-substitution. And to recognize that I need a U-substitution, the question that we're going to ask ourselves is, does the derivative of one part equal another part of the problem? And notice right away that x squared is the derivative of x cubed, right, off by a constant. If you notice, the derivative of x cubed plus 5 will be 3x squared. So they're just off by a constant, but that allows me to pick my u. So u is x cubed plus 5. Take the constant with you, because what's the derivative of plus 5? 0, and then we don't have to deal with it anymore. So du, right, take the derivative, du dx. So this will be 3x squared dx. And now compare your du with what's in the problem. So I see that I have my x squared dx, so I have an x squared dx. So I don't have the 3. So one thing you can do is say you're going to put it there. So we can put the 3 in here, so times 3. But then I'm changing the problem, right? So then we need to put a 1/3 out front. Or the other way that you can think of it is solve for the highlighted part. So you can say x squared dx is 1/3 du. And then that's the second way that you can think about it. And so now when we create our new integral, this will be 1/3, and then I still have the 5, so let's take the 5 out as well. And then my x squared dx is du, and du we always put it off to the side, so it will be du, and then e to the x cubed plus 5. X cubed plus 5 is what we call u, so I just get e to the u du. And notice that now this is a regular antiderivative, something that I can do just by looking at it, right? Is the e to the x dx. The variable is different, but it's the same concept. So I can just now say, oh, I know the integral of e to the u is e to the u. So I have my constants 5/3 e to the u, and it's an indefinite integral, so plus c. And now use your substitution to go back to x's. Our substitution is u equals x cubed plus 5. So then our final answer then will be 5/3 e to the u, so x cubed plus 5 plus c. And how do you check it? Take the derivative. Take the derivative with respect to x of your answer. 5/3 e to the x cubed plus 5 plus c. So when you take the derivative of this, I'm going to have 5/3. The derivative e to the stuff is e to the stuff, so I get e to the x cubed plus 5, and then by the chain rule times the derivative of the stuff times 3x squared, and then the derivative of that plus c is 0. So what are we left with? The 3's cancel, and I'm just left with 5e or 5x squared, bringing that x squared over to write it at the front. So 5x squared e to the x to the third plus 5. And let's compare if that's what we had in our original integral. Yep, 5x squared e to the x cubed plus 5 dx. Right, the dx is just telling us that was the derivative was taken with respect to x, which is what we did. We took the derivative with respect to x. So then I know that I did that substitution right. So some things about U-substitution. that are kind of important to keep in mind. So oftentimes U is the inside of things. So the inside of parentheses. And in the previous video, we saw some examples of that, of radicals, the inside of trig functions, so if I had, for example, something like the integral of secant 10x tangent 10x, I recognize that secant tangent is the antiderivative of this is just secant, but because I have that 10x there, I would let U equal 10x and then make that substitution. So that's what I mean by oftentimes U, we let it be the inside of trig problems. U is oftentimes the exponent also in exponentials. So like in this example that we did, right, e to the whatever power, or if you have some b to a power, right, oftentimes then you can let U be the power, so the exponent. So here, right, we let U be the power of e, x to the third plus 5. When we took the derivative of that, then we get the other stuff, the x squared dx, right, we except by a constant. We may be off by a constant, but don't worry if the constants don't match, because you can just divide out that constant and make it all work out. And right, or U is also often the denominator or part of the denominator. So like in that first example I did with the inverse tangent function, right? We had 1 over 1 plus 16x squared. So we wrote it as 1 over 1 plus quantity 4x squared, and we let U be 4x. So, but I guess this will kind of fall into the thing inside parentheses, right? I rewrote it and now I have parentheses. So following the first part, U-substitution, use often the inside of parentheses. So that's kind of some ways to find what to let U equal, but the most important thing is ask yourself the question, does the derivative of one part equal another part of the problem? If your answer is yes, then you have your U-substitution, right? Let U be the thing that you take the derivative of. All right, let's try the next example. All right, in this next example, let's see, we have the integral of quantity cosine 3x plus secant 3x, and then the whole thing square. So there's a couple of things we can do. So you can make a substitution right away for the 3x inside, or we can square everything out first, right? So this, in order to square this, we have to be careful, because this means we're doing what? Cosine 3x plus secant 3x times itself. So don't forget about middle terms. So if I multiply this out, right, I'm doing, what am I doing? Cosine times cosine, so that's cosine square of 3x, and then cosine times secant. Well, that's kind of nice, because secant is 1 over cosine, so cosine times secant is just 1, and then secant times cosine is 1 again. And then secant times secant is plus secant square of 3x, right? We don't do anything with the argument. This is like, think of it if you just had cosine theta times cosine theta, right? You would just say cosine square theta, not theta square. So simplifying this, cosine square of 3x plus 2 plus secant square of 3x. So this is what we want to integrate. So the integral of cosine square of 3x, and we can use our properties of integration and split up the integrals, plus the integral of 2x plus the integral of secant square 3x. Now 2 of these I can see right away, we can do them no problem, right? The integral of 2, we know what that is. Integral of secant square of 3x, we do have a 3 in there, so we could make a quick U-substitution. let u equal 3x, du equals 3 dx. So I don't have the 3, so we can put it there, but now I've changed the quantity, so to make it back to balance, right, to be equal, 1/3 times 3, that's just 1, so I haven't changed the problem. Or you can think of it as saying 1/3 du equals dx. So when I change this integral, then it will be secant square of u, and then the 1/3 du dx, sorry, is du. And we know that this is then the integral of secant square is tangent plus a constant. The integral of 2 is 2x. So here you still have to go back to x's. So this will be 2x plus 1/3 tangent of u. What was u? 3x plus c. So those were not too bad. What about cosine square? What is happening here? Because we can't just integrate cosine square, right? I can't say, oh, cosine cube over 3. That doesn't work because there's a chain rule in here. This is cosine of 3x, and then the whole thing is square. But I don't have derivative. If I had a sine 3x here, then I can make a U-substitution. But if I let u be cosine, the derivative of sine, and I don't have anything. So what can I do? Right now seems like nothing. This isn't one of our standard antiderivatives, right? Our basic antiderivatives. I see a secant square and a cosine, but I don't have a cosine square. So I can't do it just by looking at it, and I can't do a U-substitution because when I ask myself the question, does the derivative of one part equal another part of the problem? No, right? There's no, if I let u be cosine, there's no sine. That's part of the problem. So we can rewrite it using the Pythagorean identity. So we're going to rewrite this using not the Pythagorean identity. We want to use the half angle formula. And just to clarify, why doesn't the Pythagorean identity work? My Pythagorean identity says what? It says that sine square theta plus cosine square theta equals 1, right? So if I replace cosine square 3x with 1 minus sine square, right? So and essentially I would want to replace cosine square with 1 minus sine square. I just essentially replace one problem for another. I still will have a sine square that I have nothing to help with, right? If this becomes now sine square of 3x, I'm in the same problem. It will be sine of 3x quantity square, and I can't do anything with it because I can't make a U-substitution, and it's not a basic antiderivative. So that's why the Pythagorean identity does not help. So we want to use the half angle formulas. So what we want is, and these are the identities you want to remember. So sine square theta is 1/2 times 1 minus cosine of 2 theta. So you double the angle. And then cosine square theta is 1/2, the same thing, but 1 plus cosine of 2 theta. So these ones are not too bad to try to remember because they're only the sign is different. So if you always remember this 1/2, the 1, and then cosine to theta, and this minus and plus. Sine is the -1 and cosine is the plus. So for our case, we have the integral of cosine square of 3x dx. So this is going to become then the integral of, instead of cosine squared, we're going to replace it with 1/2, and we're going to double the angle. So right now we have 3x, so this is going to become what? So I'm going to have 1/2, 1 plus cosine of double the angle. So double 3x will be 6x dx. And now I don't have that square problem. So the 1/2 is a constant that is being multiplied, so we can pull it outside of the integral. So I'm really just integrating 1 plus cosine 6x dx. And again, here you can make a quick U-substitution, right? Let u equals 6x. But after you do enough of these, you start seeing that like, oh, when it's just a constant there, I end up dividing by that constant. So this is going to be 1/2, and then no longer the integral because I'm taking the antiderivative with respect to x. So the integral of 1 with respect to x is x. The integral of cosine with respect to x is what? So the antiderivative of cosine is positive sine of 6x divided by 6, and then plus c. So putting it all together, let's go back to, let me write the problem that we had. So we had cosine square of 3x dx plus the integral of 2 dx, the way I had split them up earlier, secant square of 3x dx. Now we integrated all the pieces separately, but we can now put them all together. So what did this one become? This is 1/2. And if you want to distribute that 1/2, you can. So it's be 1/2 x plus sine of 6x over 12, right? If I distribute that 1/2 in, plus the integral of 2, which we got 2x, plus the integral of secant square of 3x, we got tangent of 3x over 3, and then plus a constant. So this will be our final answer. So we had done the other two up here. So now I'm just combining it now that we know how to integrate cosine square. So anytime you have a cosine square and a sine square just alone in there in an integral, we want to make use of the power reducing identities. I call them the kryptonites because they reduce your power. Superman reference there. Okay, so let's try another example. This is a good one. This is a challenging one. So the integral of sine of the square root of x over square root of x times cosine root x. So not something we can do just by looking at it, right? It's not a basic antiderivative. When I say a basic antiderivative, it's none of the ones that we have written here. I can't just use the general power rule. I can't just like, oh, it's e to the x, the antiderivative is e to the x, or oh, it's 1 over x, the antiderivative is natural log of absolute value of x, or some of the other ones that we know, right? It's not something that we can do just by looking at it, so we have to figure out a different way. Either we have to rewrite it until we get to something that we can look at, or we have to use a U-substitution. So here, and in order to use a U-substitution, one question we want to ask ourselves is, does the derivative of one part equal another part of the problem? And the answer is yes, right? So then we can do a U-substitution. Now, if you don't see it, it's okay. Just take a minute, try to see like what part can I let U equal. And so one way to do this is you can let U be just the square root of x. And that becomes x to the 1/2 because I have to take the derivative. So when I take du, what do I get? So it'll be 1/2 x to the negative 1/2 dx. So rewriting that, it's 1 over 2 times 1 over the square root of x dx. And so do you see it now? There's the dx and the 1 over root x, right? I have a root x on the bottom and my dx off to the side. I don't have the 1/2, but that's okay. We can get rid of it. Multiply both sides by 2. So 2 du is 1 over root x dx. So that means that this part is going to be replaced by 2 du. And so, and the root x is going to be replaced by u. So this ones will be u, and then 2 du. So what does the new integral become with this substitution? The new integral will be sine of u over what's that? Just cosine of u, and then 2 du. So I'm going to put the du there and the 2 on the outside. And this, you can think of it as, well, that looks like tangent, right? But I don't know the antiderivative of tangent. So we're going to leave it that way, and we're going to make a second substitution. I already used u, so I can't use u anymore. So I'm going to let w equal cosine of u. Because dw, then, the derivative of cosine is negative sine of u du, which I do have in the numerator here. Sine of u du, sine of u du. We don't have the negative, but that's okay. Just negative dw then is sine of u du. And so with this substitution, the newest integral will be what? So I'm going to have my negative dw, so negative 2, the integral of then 1 over cosine, 1 over w. We let cosine of u as the whole w. So 1 over w dw. And what's the antiderivative of 1 over w? Right now, this is something that I know how to do. I know the antiderivative of 1 over w is going to be the natural log of the absolute value of w plus c. And now we just go back and substitute. We backtrack. So our substitution for w was cosine of u, so minus 2 natural log of the absolute value of cosine of u plus c. And then what was u? U was the square root of x. So then this, my final answer then will be, this is negative 2 natural log of absolute value of the square root of x plus c. Now notice that the square root of x, the domain, is already from 0 to infinity, so it's already positive. So now I can get rid of my absolute values then. So this will be minus 2 natural log of just the square root of x. Since this, by nature of the square root of x, the x has to be positive, now I don't need the absolute values in there. Hopefully that makes sense. So that's one way of doing this problem. So oftentimes you will see that with different U-substitution problems, you start with the U-substitution and then you still can't solve it, and so you need another substitution. So you can just call it something else. I called it W, you can call it V, you can call it M, J, whatever you want to call it. Now the other way we could have done this is by making a slightly more, what do I want to say? I'm thinking of the word in Spanish, substitution, a bolder substitution, right? So here I notice the question that we ask ourselves is, does the derivative of one part equal another part of the problem? And one of the things that I notice is that the derivative of cosine is sine. Also, the derivative of sine is cosine, but remember in the prior video I said we never want our du to be trapped in a denominator or inside parentheses or as an exponent, or du should always stay like dx is off to the side. So always outside the very last thing of the integral, always multiplied by whatever the integral is. So another thing that we can do here then is let u be cosine of the square root of x, right, which is cosine of x to the 1/2. And so this is a little bit bolder substitution because I'm taking a chain rule in there. So when I take du, the derivative of cosine is negative sine of the stuff, and then times by chain rule times the derivative of the stuff. So times 1/2 x to the negative 1/2 dx. And so simplifying this du, I'm going to have negative 1/2 sine of root x times x to the negative 1/2 over root x dx. And so, but notice what making this bolder substitution did. It gave us the entire thing in here, sine root x over root x dx, sine root x over root x dx. So, and be careful, don't make the small algebra mistakes of saying, oh, I can cancel those root x's. You can't, right? This is sine of the square root of x, so the square root of x here is the angle that I'm taking the sine of, versus that's just the quantity I'm dividing by. So what is our new integral with this substitution? Well, I don't have the negative 1/2, so multiply both sides by negative 2. So I'm going to have negative 2 times the integral of just 1 over u du. So notice that with that bolder substitution, I got to my answer a lot faster. And so this becomes minus 2 ln of u. U was the cosine of the square root of x. Plus e. Oh, wait, did I do that here? Oh, I forgot the cosine there. I just noticed that. So hopefully you guys caught that as well. So that changes this part. The discussion is still true, but I just noticed based on that, doing the other way, that this should have been a cosine of root x over here. And so in this case, that means we have to leave the absolute value in there because cosine can be positive and it can be negative. So, but had it been how I mistakenly had written, then we could have gotten rid of the absolute value. But had I done my due diligence of taking the derivative and checking my work, I would have noticed that I had done something wrong, or that I had not substituted correctly. So just watch out for little mistakes like that, which at first you think they're little, right? But they actually end up being quite big. You wouldn't want to do that kind of mistake on some sort of design. All right, we'll go on to the next examples are definite integrals. So I'm going to record a new video for that. So that will be part 2 of this video series.